Alright, what's up guys? In this video we're going to pick up with some calculus here, and this is going to be another integration practice video. I'm going to show you guys how to evaluate this definite integral from 0 to 4. We got hyperbolic secant squared of the square root of x all divided by the square root of x dx. So your hyperbolic functions are some of the most commonly forgot functions, and they do share similar characteristics with your basic trig functions, but there are obviously a lot of differences. One of the biggest differences is that your hyperbolic functions are not periodic like your regular trig functions. And we define our hyperbolic functions using the exponential. So in this case, the best thing to do here would be a u substitution, and there's really no ambiguity about what is the best selection for u here. The best selection for u here is obviously just the square root of x, so we will need to differentiate that. You just use the chain rule for that. It's just going to be 1 over 2 multiplied by the square root of x. Don't forget to multiply by dx. Then we need to solve for our dx part, which we'll do here. The next thing we do, I guess I'll go down here. I'll pull the 2 out. Remember, you can always factor out constants. The limits of integration are going to change since we're doing a u substitution for a definite integral. So I have to change those. And now we're just left with hyperbolic secant squared of u that we need to integrate with respect to u. Okay, so hopefully you're with me on that so far. Okay, so what we need to do now is go ahead and change the limits. We can just quickly do that. So u is equal to the square root of x. So all we got to do is plug in the 0 and the 4. And the square root of 0 is 0. Square root of 4 we know is 2. So now the new limits are from 0 to 2. Now we need to take the antiderivative of hyperbolic secant squared of u. That's hyperbolic tangent of u. But we do have to apply the constant multiple rule. So we'll multiply 2 through, and we'll need to evaluate from 0 to 2. So now this is where we need the definition for a hyperbolic tangent. So first of all, recall that hyperbolic sine, let's just start with that one. Recall that hyperbolic sine of x, that's just e to the x minus e to the negative x all over 2. Also recall that hyperbolic cosine of x, that's going to be e to the x plus e to the negative x all over 2. And much like for your basic trig functions, the reciprocal identity tangent theta is equal to sine theta over cosine theta. It's very similar with the hyperbolic function. So hyperbolic tangent of x, for example, that's just hyperbolic sine of x over hyperbolic cosine of x. So all we have to do is use the definition for the hyperbolic functions for hyperbolic sine, hyperbolic cosine, in order to find out what it's going to be for hyperbolic tangent. And since we have hyperbolic tangent of u, I'm actually going to just write everything in terms of u, since that's the variable that we're dealing with right now. So therefore, we can come up with the definition for hyperbolic tangent of u in this case, as it pertains to what we have. And so in this particular case, it's just going to end up being e to the x minus e to the negative x, all divided by e to the x plus e to the negative x. And so that's what the definition, well actually, we'll turn it back into x because I meant to do it in terms of u, but you get the point. So if we do this in terms of u, it'll just be e to the u minus e to the negative u, all over e to the u plus e to the negative u. Sorry about that. I meant to do it in terms of u down here, but I did it in terms of x on accident. Alright, so now we'll go ahead and plug the 2 in, and we'll sub in the 0 after that. So when we plug the 2 in, what will we get? So if we plug the 2 in, we'll have e to the second minus e to the negative second all over e to the second plus e to the negative second. We'll need to simplify this. And what that's going to give us is e to the fourth minus 1 all over e to the fourth plus 1. So that's what we get when we stick in our upper limit, which is 2. Okay, so make sure you do the simplification there. Now, sticking in a 0 is just going to end up giving us 0, because recall that if we stick the 0 in, remember e to the 0 is 1. So we essentially have e to the 0, which is 1. And again, we have e to the negative 0. Well, we have negative e to the negative 0. There's really no such thing as a negative 0. A 0 is just 0. So we're going to end up basically with 0 in the numerator. And so whatever we get down here in the denominator is null and void because it's going to divide out to 0. So when we stick the 0 in, it's just going to give us 0. So we're essentially just going to be left with e to the fourth minus 1 all over e to the fourth plus 1, which will now have to multiply by the 2 that we pulled out earlier. And that'll give us our final answer. So your final answer for this integral here, this hyperbolic function, hyperbolic integral actually. So we have to evaluate the integral from 0 to 4, and it was hyperbolic secant squared of the square root of x all over the square root of x dx. So we'll go ahead and multiply our constant through. So it looks like we'll get 2 times e to the fourth minus 1 all over e to the fourth plus 1, and that is going to be your answer. And that's just a number. So if you want to plug that into your calculator to see what it is, you can, but it's just a number. That's all it is. So really no need to plug it in there. But that'll be your solution for this integral here. So it's good to get it's good to work with these hyperbolic functions because again they'll come up when you least expect it. But this is pretty much how you deal with them when they do come up. Alright, so let me know if you got any questions. I'll be more than happy to talk about it. I will see y'all next time.